Hello, today we are going to talk about the Basel problem, which asks where the infinite series 1 over 1 square plus 1 over 2 square plus 1 over 3 square and so on. This problem is provided by Pedro-Mengoli in 1644. First, providing that the series converges is straightforward. Just apply the P-series test. However, finding its exact sum puzzled the mathematical community for over 100 years, until Euler was the first to try to provide a proof. First, we consider the function sin x. In its Taylor expansion, sin x equals to x over 1 factor minus x of the power of 3 over 3 factorial plus x over x of the power of 5 over 5 factorials. And then we assume it has a product representation in which alpha is its roots. Let alpha be a constant. Next, we know that the roots of sin x are integer multiples of pi, so we can express it accordingly. By applying the difference of squares formula, we can simplify it into this form. Then, we attempt to find the value of alpha. Consider the expression sin x over x when x is not equal to 0. Taking limit on both sides, we obtain this result. On the right side. On the left-hand side, we use the squid theorem to find that the limit is equal to 1. Rearranging the terms gives us the value of alpha, which we substitute back into the expression to get a final form. Now we observe that the coefficient of the x cubed term in its expression is exactly, while the coefficient of the x cubed term in the earlier Taylor expansion is negative 1 over 3 squared. Therefore, negative 1 over 1 squared pi squared minus negative 1 over 2 squared pi squared minus negative 1 over 3 squared pi squared is equal to 1 over 3 factorial. So 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus and so on is equal to pi squared over 6. Although Euler's proof was flawed in that he didn't justify the product representation of sin x, he later provided the correct proof within a few years. Nevertheless, this flawed proof paved the way for future developments.
Okay, so we need to give another correct proof to the Basel problem. So this solution is easier than other solution. It's not it didn't have too much complex operations. So our goal is to show the sum of the 1 over n squared from n equals to 1 to infinity is pi squared over 6. So note that the sine theta less than tangent theta when theta are 0 bigger than 0, less than pi over 2. So we can get a cotangent square less than 1 over theta square less than cosecant square. And we let s are real number and s are larger than 0 and less than pi over 2. So we can get cosine s plus I sine s over sine s of the power n. And by the Mobius formula, we can get cosine x plus I sine x to the power of n over sine s n equal, and we can n equals to cotangent x plus I to the power of n. And by binomial theorem, cotangent x plus I to the power of n equals to the sum of cnk cotangent n minus k of the power cross the n product I to the power of k. And we can give it to the real part and the complex image part. So, but we didn't give that n is even or odd. So we can write the last one. So the complex part cotangent is plus I to the power of n. We know that is sin s over sin xn to sin s to the power of n. So it's this one. Okay, now to be easier, we let n equals to 2m plus 1. And n is the natural number. And now we consider xr equals to r pi over n. And n is 2m plus 1. So we know that xr is r pi over 2m plus 1. For 1 less than r less than n. And sin sr, which is sin r pi. So that it is equal to 0 for all r. And now we can get the equation. 0 is the sum of c2m plus 1 2k plus 1 minus 1 to the power of n, and cotangent 2m minus 2k xr. Okay, so with the De Morgan formula, if si not equal to xj, if I not equal to j, for 1 less than ij less than n. So just like this. So every SR is different if I'm not equal to j. Okay, now suppose TR equal to cotangent square SR. So we know, from above, we know Ti not equal to Tj if I not equal to j. For 1 less than ij less than n. And now we let the polynomial pt is the sum of this one. And we let cotangent square to be the t. So NTR for all on NTR R is less than r and less than n are the roots of this polynomial. And by Vierda formula, the sum of TR from 1 to n equals to cotangent square SR from 1 to n. Equals to C2n plus 1 3 C2n plus 1 1 equals to 2n product 2n minus 1 over 6. Okay, and now we use the cosecant square equal to cotangent plus 1. This substitute into the sum of cotangent XR, cotangent square XR. So we can get the sum of cosecant square XR from 1 to n is the 2n product 2n plus 2 over 6. Okay. Now consider cotangent square XR less than XR 1 over XR squared less than cosecant square XR. And we have shown that in the above inequality is this one. Okay. And XR we have know that is R pi over 2n plus 1. For all 1 less than r less than n. And we can get a sum from 1 to n to be this one. So we have shown that. Okay, and this one will be the 2n plus 1 over n pi squared. The sum is sum. Okay, now we can product pi over 2n plus 1 squared to be this inequality. Now we take limit. The left hand side is limit is pi squared over 6, and the right hand side is also the pi squared over 6. So by squeeze theorem, we know that the sum of n squared over 1 over n squared from 1 to n when m tend to infinity. This one by squeeze theorem will be pi squared over 6, which is also the 1 over n squared. The sum from n when n equals 1 to infinity, which is the solution, which is the result of Basel's problem. So we have shown that. Okay, thank you for listening.